Okay, so we are dealing with King Kong at the top of the Empire State Building and his giant 1 kilogram penny. So, you heard the rumor that you could drop a penny and break someone's skull, so he's trying it himself. And he discovers that if he drops it like this, when it hits the ground, it has a kinetic energy of 3,810 joules, and it's going at a speed of 87.3 meters per second. Okay? But what's interesting is that if he rolls it down a ramp, say they bring up a huge ramp for him to roll the penny down, I don't know why they do that, the people of New York, but whatever, then it also has the same kinetic energy when it hits the ground, provided it's a frictionless ramp and all the usual stuff we assume for these physics problems. It hits the same speed. So let's go one step further and say, what happens if it's not just a flat ramp, but it has some sort of curvy shape, like it goes like that maybe, and then even like has a little dip like that, and then comes down like that to the ground. So same level of ground. Is the same thing going to apply? Well, the answer actually is yes, but it takes a little more work. What we've got, work, get it? Haha, okay. Our equation for work here is force dotted with delta R for a constant F. And so it worked fine here because the only force here was gravity, was just this mg. And here we had the mg, and then we had the normal force. Both of those were constant. And since the normal force was perpendicular to delta R, that part became 0. So it was just mg dot R. But what's going to happen here, because here, as it rolls down, the normal force changes. So we've got this sort of tricky situation with a changing force, and we can no longer use this simple little work equals F dot delta R thing because we don't have a constant F anymore. So what we do is and I'm not going to sort of go through the formal proof of this, but what happens, what you do if you're and you calculus people will be familiar with this. What you do when you have a situation like this is you break it up into a bunch of little pieces. So for each little piece, you say right here, this is like, say we're breaking the ramp up into little straight segments. So, well, we don't want to do an uphill segment, but say, we have one segment like that, okay, and another segment like that, and another segment that's almost flat, and then another one down like that, okay, and then, well, we don't want to do that one either, but let's just say these 4 segments, okay, and we call these 1, 2, 3, 4, and so here we've got this normal force like that. This is N1, and then N2, N3, N4. So for each section, you got a different normal force, and of course, you've got your mg going down the same way. So what you do is you'd say, work for step 1 is this normal force from 1 plus negative mgj hat, so that's that vector. So this is your total force dotted with and then like I delta r1, and then you do that for 2, 3, 4, etc. And so you'd sum up a whole bunch of these. And the way calculus people do that, of course, is instead of dividing them into a finite number of pieces, they divide it into an infinite number of pieces. And so you just do an integral. So don't freak out here if you don't know calculus. But even if you do know calculus, I'd recommend not freaking out because this is actually sort of multivariable vector calculus type stuff we're getting into here. So work along a curved path with a changing force. So this is sort of our most general expression for work. And this is the one that applies anywhere, but it's also sort of the hardest one to use, is the force, which can change as you're moving, okay, dotted with ds. This ds vector is what makes this whole thing tricky, and which is why even people in first-year calculus or have a solid first-year calculus background still probably are going to have trouble with this because this is a vector and it changes as you go. So this is what's called a path integral. I'm just going to write that down. And I want to make it clear we do not ever solve this, pretty much, unless if you actually have an integral. I mean, occasionally it'll come out with something very nice and pleasant, but most of the time, either you find a reason to convince yourself this is 0, or you take a special case where like the force is constant, and then it just turns into this equation, which is much easier. You have to understand, physicists don't like to do calculus. We don't like doing integrals. We like to write integrals. We have fun. We have parties where we'll just sit there and go, ooh, integral, integral, integral. Oh, wow, those are cool. Oh, I'm having so much fun writing integrals. But we don't actually like to solve them. We'll write them all the time. But when somebody asks us to solve them, we're like, well, hey, come on, man. Go get a mathematician, So we write them all the time, but if we ever have to solve one, we look for ways to make it simpler so we can do it without having to integrate. And if we ever have to really can't avoid it, then we tell a computer to do it. So don't freak out when you see integrals in physics. It's just that's just we like to write those. But anyway, the point is if you're doing a sort of general thing with a changing force, then this is the expression you use. Now, what I want to tell you is this ds is basically it's a vector that points along the curve you're doing or along the path you're going. So let me give an example. Say we're doing this path, okay, like that. We just have an object following, and this is not meant to be any particular equation or function or whatever. This is just some path. These represent points of the object, okay? And then the force acting on the object can point in different directions, different times. So maybe right there, it's going that way. F. But so I'm drawing these sort of going in random directions just to give you the idea. The force can be changing. Again, I wrote N, damn it. There we go. So the force can be changing as you go along. And then this ds vector is basically a little vector that always points along the direction you're going. So this is ds. This is ds here. This is ds. This is ds. So ds is always tangent to the path. And it moves along with you as you go. So at any point, you're integrating the dot product of this f and this ds. Okay, what does this mean for King Kong rolling his thing down the hill? Well, at each point, at any given point, you can think of the ramp as being the sort of smooth thing, okay? And there's going to be a normal force, which acts like that. And there's going to be this gravity force, mg, which is really just going to be negative mg j hat, okay? And you're integrating the sum of those. You're integrating the net force, which is the sum of those, dotted with ds. And ds is going along. I drew it a little bit above, but ds is going along your thing. Okay? So, to get the work, you're integrating this. What you're doing is you're doing the integral of, and this f here. So I'm going to show you that, force here. So that's for this thing here, okay? Force, total force, F net really, is the normal force minus this mg j hat, okay? Now, so the work is going to be integral, and I know you're freaking out. You're like, oh man, he's doing the integral twice. He's got to be serious about doing it. No, I'm not. I don't like integrals any more than you do. In fact, I probably like them less because I've seen more of them. Some of you, if you're taking calculus right now, you're probably in this sort of wide-eyed optimistic stage where you think, gosh, I can do anything. Integrals don't scare me. Well, they should. Integrals are scary, scary things. Okay? So, but this is our work. So this is F, is our n minus mg j hat. And we'll be dotting it with ds and integrating. Okay? So, let's expand this out. And now, this is going to freak you out even more because I'm going to be doing even more integrals. Or I'm going to be distributing and doing this integral, but trust me on this, okay? So integral, I'm going to distribute here. So this is normal dot ds, okay, plus, and actually I should be doing whatever, plus integral of negative mg j hat dot ds. Okay, so here's my two integrals because I've taken this thing and distributed it now. Okay, but this is the last time I'm going to do, well, I might write one more, but it'll be fine, trust me. So the thing is here, normal.ds, normal is always perpendicular to the surface. At any point, normal is going to be perpendicular to the surface, and at any point, ds is going to be parallel to the surface. So you have a tangent and a normal, and they're always going to be, there's always going to be a right angle between these. Always, always, always. Which means that this dot product here is always going to be 0. And you don't know calculus, but you can trust me that if you integrate 0 over any period, the answer is going to be 0. That's one of those things you can count on. So this whole term here equals 0. And it goes away. Okay? So what we're left with is this integral here. And so this is really just the gravitational force. So this is going to be W equals integral of negative mg j hat dot ds. Well, now we're back to the point. This is our force term here, right? This is our force. We're back to the point where we have a constant force. So you know what? We don't need to do the integral because we just take this and plug it in, right? So now we're back to W equals F dot delta R, where F now, instead of it being n minus mg j hat, we're just going back to this. We're taking this and making this F, which is just negative mg j hat. So now we are back to, quite simply, and I'm going to bring this, let's see, I'll do this in purple. I'll bring it up to here. And work is now simply force negative mg j hat, because we proved that the normal force doesn't matter, so we just got the gravity dotted with delta R. Now delta R, what is delta R? Well, delta R, remember this thing, I'm going to use blue for this. So you're going from this point to this point. So this vector there is delta R, right? So you've got this vertical component here. So delta R equals negative h times j hat, right? Because you come down a distance h, that's negative j hat. And then something times I hat. I'm just going to, for the hell of it, I'm going to call it d. I just, for no reason. I'm just picking d plus d I hat. But it's not going to matter, because when you dot this, when you plug this in, your negative h j hat plus d I hat, and dot it with this negative mg j hat, what you're going to get is that the work is, once again, you're going to get this negative mg j hat times negative h j hat. So you're going to get mgh, and then this term doesn't get dotted with, when you do the dot product, this term just goes away, because it doesn't have a friend in force. There's no I component of force. It's gone. So once again, rolling down this ramp, which has some arbitrary shape, the work is just mgh. Once again. And that's really sort of the amazing thing about energy, or one of the amazing things about energy, is that it's path independent. Or in many cases, it's path independent. If you can show that there's a constant force acting on this thing as it moves, and there's no other force, changing force perpendicular, it's not. Well, look, it works for gravity, okay? And it will work for many other things. And I'll show you what kind of things it'll work for. But what's really important to get out of this is we didn't say anything about the shape of this thing. This could have been, any complicated shape we wanted. In fact, it could have been, I'm just going to draw another possible shape in brown. It could have come down and gone up and down and up and down, and then even like done a loop and gone woo, and then come back, and then come down here. And you would still be able to use kinetic energy to calculate, using the whole energy balance to calculate what the speed of the thing at the bottom, or what's kinetic energy at the bottom would be, and it would still be mgh. That is what is really powerful about energy methods. Now, what we don't have here is how much time it took. You can imagine that, it takes some time for the penny to fall, obviously. You can imagine it's going to take longer for it to go down this ramp. And if you have a curved ramp or a shallow ramp or this weird loop-to-loop ramp where it keeps going around forever, it takes a long time, it's going to affect the amount of time it takes to get to the bottom. But it doesn't affect the speed when it gets to the bottom. So if you don't care about the time it takes, and here we don't, energy methods can be enormously powerful. So that's the lesson I want you to take away from